So one thing that hasn't been solved yet on the Game Gears is the VA4 and VA5 revisions of the board, often called the Majesco boards. These were the newer boards near the end of the life cycle, where they made things cheaper. A different company took over and made a cheaper version of the Game Gear. So all the screens on the market right now, mine, McWill's, Ben Ven's, everybody else that have made them, doesn't have support for VA4 or VA5. I managed to get this VA5 board sent to me so that I could take a look at the interface, but it's sat on the shelf for a month or two now, without any real work being done. Ben Ven, you may know, he's also got a Game Gear screen now. He's got his hands on a VA4 and VA5 as well, and he's been working on the interface for a few weeks. I saw on the Discord channel over the last few weeks he's been making good progress and seems to be near the end of completing the interface. I did see that he was struggling with some data inversion, and I thought I'd just step in to see if I could help. So yesterday I got this VA5 board out of stock, probed around with the scopes, figured out what the pins were, and had a look at the interface. I fed back this info on Ben Ven's server, along with Ben commenting where my investigation led me down the same route as his, and where his investigation was different than mine. It was important to make sure we did independent testing and didn't tell each other initially what pins we'd used, what presumptions we'd made, so that we didn't give pre-assumptions when we're trying to reverse engineer the interface. Once we were close enough, we collaborated more and figured out what matched, what didn't, and helped each other solve the problems. It's quite an interesting thing to see that two independents have found almost identical information, made almost identical mistakes along the way, and come to very similar conclusions. And it's a good thing to do. When you have good open collaboration on projects, you help each other out. Ben certainly helped me with my understanding of the interface, and I hope I've also helped him along the way with a few little bits he was stuck on. So what I'm going to do is, firstly, I want to reverse engineer all of the Game Gear boards, the Game Boy Advance boards, most retro consoles. I'm going to start by stripping all the components, scanning them in, redrawing the PCBs, and then open sourcing all the schematics and the PCBs so people can make them and use them for diagnostics. On top of that, you may know I've started a wiki page, RetroSix.wiki. This is aimed at giving away all this knowledge to anybody that wants it. And this is going to include the VA4 and VA5 Game Gear interface, which I'm going to discuss next. So I'm going to explain to you how this VA4 and VA5 interface works, as far as I understand it now. Bear in mind I've only been working on it since yesterday, and I haven't actually got an image on screen. However, Ben has been working on it for a few weeks and does have up and running code that shows it on screen. So between us, I'm pretty sure the understanding we have so far is very accurate, and we can show you this. So let's just take a look at this board first, and I'll show you where I started, and then we'll take a look at the logic analyzer scopes and explain how this works. So let me just bring over the scope. So you can see here we've got a Game Gear board. Looks fairly standard like all the rest. I've got a logic analyzer already hooked up, so if I just turn this over slowly, you can see down the bottom corner here now, or if I go to the center a moment first, you can see here it says VA5 upside down, because I've got the console upside down at the minute, but this is a VA5 board. The telltale sign is typically down here. We have this sort of resistor grid array here, just a chip that's got a bunch of resistors on. I'm not sure whether it's got a capacitor on or not, but there's certainly a bunch of resistors on. And this is a VA5. The VA4 I don't have, but from images, this resistor array is horizontal rather than a square. So we have the VA5 board here. The first thing I did was just hooked up the oscilloscope, powered up the console, and started probing along these pins down here. You can even see some solder points where I've been attaching wires to the traces. Now, because I know how the Game Gear interface already works, I kind of knew what I was looking for. I knew I was expecting a horizontal sync pulse of a certain width. I knew there'd be a vertical pulse that happens 60 times a second. And I knew the general visual of the data if it was anything similar. This is also the main ASIC, so the main CPU, if you will, here. So we only have to really probe around the area. I also know from the previous Game Gear boards that there's normally resistors and capacitors here on the data lines, and that these lines also go along here to the LCD. So all the signs of where the data is likely to be happening is, I just get some tweezers, no, we don't have any here, is these pins here. You can see them all coming into the CPU. So the likelihood is all the data we need is down on this channel here. So I just probed along with the oscilloscope until I found signals that looked right. If I was struggling, I could also peek under the LCD and probe all the LCD pins, because we know the LCD interface must go to the LCD pins. Luckily, I found them through probing and realised once I'd tacked onto a few pads at the bottom of the CPU, they nearly always went to this resistor array. The likelihood is these are the termination resistors on the lines. And so if you look at this device here, the screen device, you can actually see that all it is a bunch of carbon resistors directly on the surface. So those little black squares, those black rectangles, are resistors. They might be capacitors on some, but so far I think they're all resistors. And you can see they basically bridge two pins. So one side of each resistor goes to the CPU, like these legs here, and the other side goes off to the LCD. So from that, I realised that tapping onto one side of each resistor gave me most of the signals I wanted. So what we have in order here, if I remember rightly, is this pad was the pixel clock, this is horizontal sync, and then what I've labelled here is D0, 1, 2, 3, 4, and 5. So we have 6 data pins here, as opposed to the typical 4 on the other Game Gears. So we already know the interface is going to be different because there are 6 data lines and not 4. And then one thing I'm missing on here at the minute is the vertical sync. I'll just go and solder that on before we do the next part. I believe vertical sync was somewhere down here on the first sort of 10 pins, somewhere there. So I'll connect that up and then I'll show you the scopes next. I'll detail all this on the wiki page so you can have all the pinouts, where they go, as well as all the detailed scopes. But this is the general connections I've made. I've connected them up to a Salia logic analyzer. This allows us to see all the data in real time, and that's what we're going to do next. So let me just solder on the VSync pin on here, connect it up to the logic analyzer, then we'll jump over to the PC and I'll talk through the interface, how it works, what you're going to see and what you should expect. So you can see we've got Sonic running here. Ignore the partially broken screen, that's just how it is because the tape came off the bottom when I was testing things. But you can see the screen in general and what we want to capture. So let's just leave that screen where it is for now, and we will just capture some of the data and show you the general view, and then we'll come back and try and capture and analyze a specific part of the data to check we have the interface right. So I've got the Logic Analyzer software running at the minute, and I've labeled all of the pins down here for easy reading. So we have VSync, HSync, pixel clock, and 6 data lines. If we just click capture on here and press stop, we can now see the data we want to see. So if I zoom right out, you can see this is the general view. Once you get used to video signals, they're all very similar and you'll kind of get a grasp for what you're looking at. But say you didn't know what you were looking at. Firstly, you want to see if you can find the details on the Game Gear, what refresh rate it is, what screen size it is, that kind of information. It would help you scale this data and see potentially what you're looking at. Now I know the Game Gear is 60 frames a second, and the one I've labelled VSync up here, as you can see, says it's 16.68 milliseconds. So if you times that by 60, that goes into 1 second, 60 times. So this is a frame every time we see this VSync. This is running a new frame every time. So this indicates every time we hit this pulse that there is a new frame drawn on the screen, or at least the data has been sent to the screen. The way that the data works is typically you listen out for a screen refresh here, so this is a new screen, and then after that you draw your lines horizontally, one after the other going down. Now the Game Gear's resolution is 160 pixels across, so per line, and 144 lines down. So the next thing we want to look for is the horizontal sync, which is how many times we are drawing a line. If we zoom in, so this is still a full frame, you can now see this H-sync here. Every pulse on these is going to be a line. So for example, if we zoom right in, this was the start of a frame. So this down here is a single line. So this is line 1. Then this up is line 2, this down is line 3, line 4, line 5, line 6, 7, 8, 9. So if that was the case, we should see 140 of these ups and downs. So you'll see 70 of the downs and 70 of the ups. If we were to quickly measure that, starting at the start of VSync here, dragging across to where we can visibly see what looks like the end of the data, we can see we have 74 downs and 73 ups. So this is slightly over when you double that up. That's 147 or 148 potential lines. So that will mean there are a few lines left and right when we come to visually check the screen that will be porches that aren't used. And if we look, you can kind of see this is probably a porch not used, and the end one is probably a porch not used here. So we can tell that we have a full frame here and what looks like a full set of lines here. So all the lines needed to go down. Remember, the resolution's 140 lines down, and we have just over that with the number of clocks we see. So that slight difference we can see when we put it on an actual screen and find out which part of these lines we ignore. So there might be 2 at the front, 2 at the back, but that's easy enough to see. You'll find the main data when you come to do the coding, and you'll see it on screen, and then you can iron out which few lines in the signal are not needed. For example, it might not start until you rise, and then the first line of data might start here. But that's easier to see when you have the final code running. So after you've got the vertical sync for a full frame, and the horizontal sync for every line in the frame, you can now focus on individual lines. So this indicates here where the frame starts. This indicates potentially line 1, if not it's somewhere close. So we'll say this is line 1. And within this line here, so within this 63.5 microseconds, we should see all of line 1, which is 160 pixels across the screen. So within this, we need to find 160 pixels of data. This looks like it's all white because all the data lines are high for the most part. This one's low. In fact, we might just have a bad data line there. Yeah, I think D2's just come off. So let me just see if I can connect D2. There we go, just recaptured and connected. Now we have D2. So if we zoom in and say this is the first line, we can see as we zoom closer this pixel clock, which is the next thing. This should be clocking out, as it mentioned, usually the pixels of the screen. So this horizontal sync, this drop here, this 63.5 microsecond period, is representing a full line. If we zoomed out, because the entire frame starts here, it means the first line starts here. So this is the first line, as we mentioned, this is the second. So we zoom in, and we can see this represents the first line, which should be 160 pixels. So now we've got to figure out within here, where are the 160 pixels? Well, normally in a video signal, again, if you look up sort of VGA signals or HDMI signals, any kind of video signals, you'll typically find they work on porches, where there's a quiet spot before or after or both on a video signal to allow you to process that data. So quite easily, this 16 microseconds here and the sort of 17 microseconds here look like the front and back porch of the video signal, meaning that even though we're in a line here and we're clocking out data on the pixel clock, this part of the signal is likely nothing. And same here on the extra part of the signal. But let's say we presume data is within the entire horizontal line here. If we just quickly draw and measure how many clock pulses are within the signal, you can see we get 256. It's similar to NTSC video standards. So this is representing potentially 256 clocks of data per line, but we only have 160 pixels. This is a Game Gear game, not a Master System game, so we can come to the Master System game another time, but this is just a 160 pixels we're after. So we know for a fact there are too many pulses here, and it could be that we ignore pulses. For example, in the VA0 and VA1 of the Game Gear, you have 3 clock pulses and then a value. 3 clock pulses a value. You don't actually process every clock pulse. But in this case, it looks more obvious that this is the front and back porch, and the data is quite visible here. If we check another few frames, and you look for something similar, you can see, looking between this gap, you've got the same 16 microseconds on every frame. It's always blank. And if you zoom out and scroll along to a completely different frame, zoom in, you can see you always have this 16.39 microsecond delay. So from that, I made the presumption that this bit of information is ignored. And again, this is because it's similar to the VA0 and 1 of the Game Gear that I've worked on. So if we were to measure how many of these clock cycles we should ignore before real data appears, we can draw to here, and you can see we get 67 clock cycles. So that means there are 67 falling edges. So the horizontal line starts here. If we zoom out, you can see the horizontal line starts here. After the horizontal line, the pixel clock then falls. So that's the first pulse. And you can see the data starting to set up here as well. So we ignore the first low pulse. We continue that all the way along until we get to the 67th low pulse, which is here. You can see here, this is the data setting up now. And the data, whatever it is, which we haven't figured out just yet, these data 6 lines, you can see them clearly setting up. So it looks like on the 67th low pulse of a new line, data starts to appear on the line. Now we sample the data by the looks of this, and what I thought originally was on one edge of the clock. So I figured we'd sample the data on the falling edge, which means down here. And then you typically let the clock rise, come back down, and sample again here on the falling edge. So we'd have the clock data, which this is pixels of data, so this will be your red, green, and blue information somewhere in this data signal here. You would normally sample them on the falling edge. So if we make that presumption that we start on the 67th down, which is here, and we want to now count how many times we see data in this field of data here, we'll just put another marker on. We'll come over. We'll zoom in to where the data seems to finish, which seems about here. Maybe as the last data, it could be here, but it looks like it's going to be this one. You can see we've got 121 falling edges and 120 rising. So if the last data was here, it would be 120. So that means we have 120 cycles of data. Now on the Game Gear VA0 and 1 LCD interface, which I've broke down and explained on RetroSix.wiki already, it's 4 bits of data per colour. So that means there's 4 digital bits. So for example, it could be D0, 1, 2, and 3. This would be 4 bits, and every clock would be, say, the 4 bits of the red. Then the next clock would be the 4 bits of the green, then the next clock would be 4 bits of blue. That would then give you 1 pixel in the line. And that would be called 12-bit colour, because you have 4 bits from red, 4 bits from green, and 4 bits from blue. If we work on the presumption that this is still 4-bit colour, that would mean we need 12 bits per pixel, and there are 160 lines. That would give us 1,920 bits of information we need to fit within this 120 clock cycles. We have 6 bits of possible information, so we can simply do 6 bits times 120, and that gives us 720 bits of possible information we could store within here. So that isn't enough information for the whole line. Now Ben Venn had already been working on this, and I noticed he mentioned he believes it's 3 bits of colour. So if we work on that presumption that the 3 bits of colour is right, we can again do 3 bits of colour for red, green, and blue, meaning there's 9 bits per pixel, over 160 lines, gives us 1,440 bits that we need to fit within these 120 clock pulses. And again, as we know, we have 720 possible bits of information, which is exactly half of the required 1,440 bits. So this seems like we're getting somewhere and it's right. Now my presumption on this was that this video signal will be displaying half of the information on one frame, so half of the information over an entire frame of information, and then the next frame is the other half of the screen. And I was thinking along the lines of an interlaced video. I broke this down on the Ben Venn Discord, showing that all the data could actually be extracted this way, and that visually, from what I'd done, it looks like it was correct. Now this is where Ben Venn helped out and said that the data is definitely all within each line, and it will not be interlaced data. And the key was, we don't sample on just the falling edge, we sample on the rising edge as well. So that means we sample the pixels here, and then we also sample the pixels here on the rising edge, and then again here on the falling edge. So this now means, over this frame of information, we have 120 rising edges and 120 falling edges. So now we have 240 pulses in this line. Again, 240 pulses times the 6 bits of possible information we can store is 1440 bits of information, which is the exact number of pixel data we need to make 160 pixels of 9-bit colour. So it looks like we have all the information we need here to extract the pixels. This also means to read the data, we now have 6 bits of information, but we have 3 bits per colour. So what is likely is you have 2 bits of colour, potentially red here on the first 3, green on the next 2, and then the next clock cycle must contain the missing colour in the first 3 and the start of the next colour in the next. So effectively we're fitting 2 colours per clock cycle when we need 3. We need red, green and blue. So deciphering the exact information in this data is quite tricky. You can make presumptions, but there are a few ways of doing it. The way I've done it is simply to start with a specific screen in Sonic and look for the known data. So let me just turn the console on and off and show you. So if I just power cycle the console and I wait for the white Sonic screen to appear, so here, and now if I press capture and stop, I now know what I've captured here is the white screen with the Sega text. So we can pick any line. We can just zoom in anywhere because this was all the same screen. We can see the start of a frame here. And we can see now what should be line 1 here. So all these, so you imagine this is line 1, 2, 3, 4, 5 going along. These should all be pure white data. And then when we get so far in, you should start seeing the Sega logo, which looks like it's here visually. And then we can see the white data below. So you can kind of visualize when you zoom out. You imagine if you tilted this and rotated it 90 degrees and looked at this as a screen 90 degrees rotated. The top left here going to the bottom right down here. You can see that this looks like all the white area. And then you can see this looks different. There's more information in it. That will be the Sega logo. And you can see this as the white on the remaining edge. So what I did was then grab an emulator, open up the exact same game, and screenshot the screen we're looking at. This gives me the ability to use Photoshop now to find out exactly what pixel is what. So we can see straight away that we have a lot of white pixel, and we can double check by clicking. Now it's only 3 bits of colour, so even though this isn't showing pure white, it will end up pure white when it's converted to 3 bits. So we have a lot of white data, and we can also see that the size of the image is 160 by 144. So we know these are the lines of data we'd expect. What I'm interested in is, firstly, if we take a look at the overall frame here, we can see that we're expecting these to be white data. Now, firstly, if we zoom in, we could see if these dots were all 1s here, so on the second line, all of them are high, that would make sense because that means all of the data within the line is just entirely white. But you'll see what's happening is every other line, so bear in mind every down and every up in this case is a line. The first line, when the data starts here, ignore this little glitch here, this is just a bad connection on this specific board I have. This actually just goes down and this ripple is not really any trigger. So this is a false trigger here. So all the data lines go down here and they're all low. So they're exactly the opposite way that they should be. This should be white, so they should all be high. But you can see that every time this H-sync goes up and down and up and down, the data also seems to change from going high to low to high to low. So this looks like the data is inverted every other line. We'll touch on this again in a moment once we've cleared everything else up. But in general, we do seem to be able to see that we have white data, whether it's inverted white, then solid white, inverted white, and so forth. The lines do seem to be white data. Now we could figure out the true starting point of the first line, because what we're going to do now is go to Photoshop, select right the way down to here. So you can see this now is the number of lines that should be white. And you can see there was 48. If I drag the cursor again, if you see by my cursor, I know it's tiny, but it says 48 pixels. I could also copy that information, start a new document, and it tells me it's 48 high. So we know we should have 48 lines of white, and then the next line should have 38 pixels of white before turning to blue. So let's first clarify if we have 48 pixels of white data. So I would expect it to stop around here, which would also mean we should have 24 ups and downs, because an up is one, a down is another. So if we just measure from this, which I presume is the starting point here, so this would be the first down trigger, going across to where I'd presume this trigger here on the up is the 49th line, because here's the color data. So if we go to here, you can see we have 25 downs and 24 ups. So that means we are on the 49th line here, which is actually still looking like white. So that means we are one out. That does then potentially mean that it goes down and the first data line is actually here, or at least the first visual line is here. So if we were to drag this in, so we ignore this line in essence, this would give us 48, which would mean the 49th line here that shows hopefully the color information looks correct. Now again, figuring out the very first line, whether we missed the first one for any reason or not, we can worry about when we get it on a screen and running. But for now it looks like we're close enough within one potential up or down. If we're going to go off what we see in the screenshot, it does mean that this first line should be ignored based on that fact. So now let's go to the line we care about. This should be the 49th line of information. So this screen here we see should correspond exactly to this line here. So now what we should see is 38 pixels of white going over, and then the blue. So if we work out how many bits that would be, how many pixel clocks, we know every clock there's 3 bits and 3 bits. So let's first just work out 38 pixels, and we know the 9 bits of pixel now. So we know there's 342 bits that we need to cover before we touch on the blue. We divide that by the 6 bits we get every clock cycle. That gives us 57 pulses. So on the 58th pulse we should start seeing blue. Again, we can prove that by measuring from here to here. And I believe the data starts right after the H-sync changes. So here's the first bit of information. And if we zoom into where we think the first bit of blue information is, so we want to go one before. Remember, we want 57 pulses before we then get to the what looks like blue data here. Remember also I said there was 67 pulses of nothing data. So if we went back to say the white here, and we find what we believe is the start of the data, we can add something here that is 67 fulls. So instead of doing the 94, we should first do the 67, which is where we believe the starting point is. So that means we believe the starting bit of information is here. We can then see how many pulses we have before we hit the blue data. And you can see from that, so before we hit the data, we have 28 rises and 29 falls. So if we do, we're after 57. So if we do 28 plus 29, you can see we get exactly 57. So that adds up that this is the blanking area, the bit of data we ignore. So this is your 67 pulses. This is your white data here, which is this. And that leads us to finally what we see here, which should be the blue of this Sega logo. And then if we zoom out more now, and let's just zoom out to this frame and let's take a look at something. So if I just screenshot this information, we can see quite clearly this area here is the white. This area here is the blue. This is the white. This is the blue. This is white. This is blue, white, white, blue, blue down here, which is getting messy, white up there, blue down there, white up there, blue down the bottom, and finally the last white. So you can see we have visually the data that looks like this line, even if you know nothing more than the highs at the minute are white, and you can see just the white areas, and the general size of the data looks correct. This gives you a good visual that the data is there in a format similar to what you're expecting. The fact that you can actually count the lines and get to a specific spot and see the data all falls within this shape. So this is the kind of breakdown I've done to see that information. So if we now go and we expect to see this pixel next, that means this bit of information now, and we're going to have to use 2 because bear in mind I mentioned there's only 6 bits of info here and we need 9 per pixel. We should expect to see red, green and blue somewhere in these first 2 pulses. So if we screenshot this and bring it into Photoshop, and again we now look at what we'd expect to see. First we need to know what should this colour be. So if I sample this colour from an emulator, and we can see it gives us a red, a green and a blue value. So it's telling us that the red, if we go to Programmer and Decimal, the red is 34. You can see in binary here, I don't know, you can actually, it's really small, but in binary here, there are 8 bits. So this is 8 bits of colour, which at most is 255. So if we typed in 255, you can see 8 bits as all ones. So it's telling us that the red channel is 34 in value. Now to get a 3-bit colour, all you have to do is blank out the least significant parts. So if we had, for example, 255 as a colour, so pure white, the binary of that is 8 ones. If we wanted a 7-bit colour, this would then be 254 as a true value. You want 6-bit colour, you'd remove the next bit and it would show as 252. So a 3-bit colour, you need to remove the lower 5 bits of information and simply set them to 0. This would mean that you're representing pure white as 224 in 3 bits of colour. You can't show 255. So if we plug in 34, which is the value it's telling us the red in this pixel is, it wants 001 and then we can ignore everything below it. So that means what we're really going to see on screen is 16. So we could actually change this also to match if we wanted to see the real colour, what it was going to end up as. And then green is 50. You do the same, go to decimal, put 50 in. It's 001 and then everything below it's ignored again. So these two are equal, they'll be 001. And then blue is 185. So if we plug in 185, you can see the most significant bits here, 010. We would care about 101 only, and everything below it's gone. So if we were to put in 101 and then the remaining zeros, you can see we get a value of 160 decimal. So if we were to put in 16 and 160, this is now your 3-bit colour representation. So if we were to get a paintbrush then and just paint over this size, you could see that this is the blue that will be represented on screen. So it's very similar, but this is how 3-bit colour would look. This also lets us know that the colour we are looking for is 001, 001 and 101. So this is the information we are hoping to find within these 6 bits and these 6 bits. And I'm presuming it would be the first 6 bits and the first 3 bits of the next pulse. So if we firstly just decode what we see here, D0 is high, so it's 1. D1 is low, so it's 0. D2 is low, so it's 0. D3 is high, so it's 1. D4 is low, so it's 0, and D5 is low, so it's 0. So that means this line of information here looks like this, 1 0 0 1 0 0. Now that can also look like 0 0 1 0 0 1. This could be coincidence because I have no idea of the order of these bits yet, but it does show that the data is there. If we were to then clone this over to the next line and do the same, the D0 is high again, so it's 1. The D1 is high again, so it's 1. The D2 is low again, so it's 0. And then the line below, which possibly is the next pixel, which would also be blue, is 1 0 0. Which makes sense because the one before was 1 0 0. So what we could have here is this could be representing red. This could be representing green. And this could be representing blue. This would fit within these values we need. It would also mean that we could juggle D1 and D2 around so that this becomes 0 and this becomes 1. And these zeros don't change. This also isn't enough information to really find the pixel order, but the pixel order is fairly easy to find when you finish coding and you just swap these 6 bits around until they match. I could carry on further and analyze the signal, and we could pick, for example, this more specific blue or this red and go to this exact pixel in the same way, and then find out what order they come in to see if we find all the bits within the data. But what it does look like is this order is generally correct. And it means this next bit is possibly red, blue, green. So if we just go 1 pixel further, this would be half of 1. Let's just clone this over and do the same again for this side, and let's see what we get. So we have 1 0 0 1 0 1. So if this was going to go red, green, blue again, red would possibly match, green would match, blue would match. So it does seem like it simply goes red, green, blue, or green, red, blue, and this is the order of data I would expect to see. This means that every one of these is the pixel color, and as we go along, we can simply decrypt all this to get the full line of color, and then go to each frame and find the entire image of data. This is then fairly easy to chuck into an FPGA and make the code work, and that's something I'll do for the clean screen and something Ben's already doing for his Game Gear screen that he sells. I'm pretty sure by the time this video is out, he will have his code up and running and ready to sell. And you can probably expect mine to come in a month or so. I'm busy on a few other projects at the minute. But this is basically how the VA4 and 5 seem to be working. If I pull up an image that Ben shared, this is the data signal. So if we look at the data signal we've got, this is the data signal that Ben shared from his investigation. You can see based on numbering, again, generally it's red, green, blue, red, green, blue. So it follows the same principle that we've written here. So both of our investigations led to the same general rule of how the data is stored within the frames. Now this leads me back to the reason I took a look at this yesterday, and it was to try and help out on a problem that Ben had mentioned he had, which was data inversion being wrong. Now bear in mind I knew nothing about anything yesterday on the VA4 and 5 boards. I literally started looking at it yesterday. But I did mention at the start, notice that this is the white area, and this is one of the first things I saw and just presumed something very obvious. When we zoom in and see now what we know is the data, because we've just proven it by looking at a certain line here, we know this is the data of the screen, about central to each horizontal pulse. And we know that these first lines are all white because they represent all this white area up here. We should be seeing on the pixels, for example, the first line here, or let's skip to the third just in case this one isn't red. The data should be around here. And it should be all ones because it's white. And yet it's all zeros. But I mentioned my presumption was simply that every time HSync is high, the data is normal. Every time it's low, the data is inverted. If we look along the whole frame, this seems to be right. And I didn't really think anything past that. But then Ben mentioned that there is an issue and that some of the signals won't conform to that logic. I did a good few frames before I realized it was actually the case. So what we actually want to see is the opposite. When H-sync is high, the data is low. So let's keep looking a minute, see if we can find one. And I mentioned before, it did actually take me a while to find one. I presumed this was just normal and that every frame was always this way. And there we go, we've found one here. So there we go, this frame. Let's tag this one. So we can see here now, when the signal is low, the data is high, and when the signal is high, the data is low. If we compare that to the first find, we can see when the data is high, when the H-sync is high, the data is high also. So H-sync and data being pure white are matching in this instance, so high, high, low, low. And when we go to this frame, you can see it's actually the exact opposite. So when it's low, it's high. When it's high, it's low. I didn't spot this, and this is something Ben told me to look for, and we found the issue in these scopes as well. That then led to the point of why I started looking at this, was to try and to help find how this code is inverted, because clearly the data is still correct. The confusion is simply when on a line do we invert the data, so every time there's a 1 there's a 0. If we don't do this, the screen randomly changes colour to be complete inverted. So this is something we looked at this morning, and I feel we're at the conclusion of it, and between us we have found the solution. I spotted something which is on this pixel clock. There is this extra sized pulse just before a line starts. If we zoom out, it's at the start of every line. So the key was, does this indicate the status of whether the data should be inverted or not? So when we look here, it's a high. And if we zoom out, and this is the one with, bear in mind, an inverted logic on low, has a high signal here. We zoom out and go to the other frame over here, and we go to the first line, the first logic, you can see this time the extended one is down, indicating the opposite, where when it's low, it's the same, and when it's high, it's inverted. Now, you could get confused because every single line has this pulse, but the key to the inversion seems to be that you only read this pulse on the first line of the whole frame. So here's the entire frame of data. If you zoom in, these are all the individual lines, and every individual line has this slightly long pulse. But if we always read that piece of information on the first line, so this specific line, and use that as the status of whether to invert the data or not, that seems to be the solution to whether or not to invert the data across the whole frame. We're still testing this theory, but hopefully it'll be right. If not, we'll figure out what it is. And then I'm going to follow this up with written documentation, screenshots, and a write-up on RetroSix.wiki, fully explaining how the Game Gear VA4 and 5 interface work. So you can see if you go to RetroSix.wiki, I've already written up the Game Gear LCD interface, and this is my first understanding when I did the clean screen of how the VA0 and 1 interface work. You'll notice very similar traits, whereas however here the pixel clock is read on the rising edge, and then it ignores a pulse, then it reads the red first, then the green, then the blue over a course of 6 pulses. So it's quite a different interface, but overall looks fairly similar. I'll do another write-up on this interface, and hopefully between us, me and Ben should have this interface worked out and on a running board. I'd like to give Ben credits where due. He's certainly helped me understand this interface in the last day or two. And if you jump on his Discord, you can see the thread kind of starting in the Game Gear LCD channel. Ben posted this information that this is the VA4 or 5 board running, and you can see it's almost there. There's just a bit of white at the side. And mentioning that something might be slightly off. This obviously piqued my interest then. I've had the board for a while. You can see I was intrigued because it seemed like then the VA4 and 5, the Majesco boards, were potentially 9 bits of data, not 12 for the colour. So that's what made me want to have a look at this and see if it was right. So I'll start off asking here just for some info, and I'll do a scope when I get back from holiday, because I was on holiday last week, helping out with some other stuff, and mentioned that he does feel it's 9 bits, and that he's done quite a bit of testing on it. So you can see when I get back from holiday, if we scroll down, Ben sends me some test ROMs he's worked on, which will be perfect for helping debug this code. If only I could get it working, but at the minute I can't due to it not working with an EverDrive. These would be really handy to help see the video signal clearly. Instead, I've had to do Photoshop, screenshotting an emulator, and reverse engineering the color bits, as you've just seen. But these would be really good if I could get them working. I then get back from holiday yesterday and start quickly probing around and scoping the board. I found the pins I mentioned, and here's all the scopes of me going back and forward, sharing what I've found. Here's kind of a big write-up on my presumptions of calculations, where I actually think it's interpolated data. Similar screenshots as I've just shown, converting the colours to 3-bit, how we find the areas, how we decode the bits, and you can see here my presumption as we read on the falling edge only, and I'm actually missing the data between the lines. And this is where Ben helped out and corrected me that it's actually read on every other up and down. And then I go through, make all the presumptions, feel I've got it right, go sit down with my pug and enjoy myself, and then Ben helpfully points out that I'm actually wrong in quite a few spots and works with me for the rest of this morning to correct my assumptions, and then we both work together on trying to solve this data inversion problem, which I'm pretty sure we've figured out, but it goes on for a good while, chatting this morning about trying to figure out, sharing thoughts of how they work, helping each other prove and disprove our own theories, and it was a good session to really figure out what's going on. So anyone that wants to kind of learn the Game Gear interface, I'd definitely jump on BenBen's server. I do a lot of chatting on there when it comes to the hardware side. And you can also visit RetroSix.wiki for the complete write-up of this. But hopefully this will help anybody that has a Game Gear board or anyone that wants to make one to be able to support VA4 and VA5 going forward. And you're all free to use this knowledge. Just remember, due to credit, I'd say myself and Ben if you're going to use any of this information. Ben more so because he started this before me. I've simply jumped on it yesterday, figured it out, and he's helped me to rapidly confirm my assumptions are correct and work with me on understanding the protocol. So big thanks to Ben on that. It's been fun working on. And if you guys want to see any other LCD interfaces reversed, or you want me to work on any other project to help you understand it, just let me know. I hope this was useful, and I know it's quite technical, but for those that are generally curious of what this is, what it does, and how LCD interfaces work, I hope at least you took something from this and you can kind of understand what's going on. For those that make Game Gear boards, I hope you do start supporting VA4 and 5 in the future, and it'll help the community much more.